Good morning, students. Welcome to the second lecture of the second chapter. We are studying it, the second chapter, structure of atoms, which is also termed as an atomic structure. In our first lecture, we discussed it, how the atom is symbolized. In this lecture, we are going to discuss something different. What are isotopes, isotones, isobars, isoelectrons? What are they? When we are having it as an atoms with something different about the proton, neutrons, electrons and mass number, then they are termed as in specific compositions. Like the first one we are going to study, isotopes. Now remember, I am going to always change the suffix. Iso means same. Iso, it means same. So here what we are going to get the same. Isotopes, something is going to be same. So here the word we are writing it, isotopes, means atoms having same number of protons and different atomic mass number. Or you can also say it as atoms having same number of protons and different number of neutrons. That means the word iso is over here specifically for number of protons. When we are having it as in different atoms, means the presentation of the atoms are there, but those atoms are having same number of protons. Now when we are having it as in same number of protons, it means the symbol is going to remain same. It's having it as a same atom, but we are having different atomic mass number. You can say it as here protons 1. It's have same number of protons, but if I go it for atomic mass, I am going to get it as different. Or if we calculate the neutrons, we are going to get it as a different number of neutrons. Same protons but different atomic mass number or different number of neutrons. So they are considered as an isotopes. The second term, see again the word I am not removing it. Iso means same, but this time I don't want the same number of protons, something different. So the word is termed as isobars. The bars means we are having it as an atoms having same atomic mass number but different atomic number, that is different number of protons. It's having same atomic mass number. That means, for example, we can write it as argon 1840, potassium 1940 or calcium 2040. So what does it show? Mass is same but atomic number is different. So that means protons are different. Atomic mass number is same. So they are considered to be as an isobars. Right? In isotopes, we got it as same number. Isobars, we get it as same atomic mass. Right? The third term, that is isotones. Right? iso, the word is I'm putting it, I'm not even erasing that name. Iso means constant, isotones. So here what is going to be constant? Atoms having same number of neutrons. Their mass number, that is atomic mass number, or atomic number are different. Their atomic number or atomic mass number are different, but the number of neutrons are same. That means you can say that N A minus Z are same. A minus Z is same. For example, let's take it as K1939 and Ca 2014. So what we are going to get it here? P19, here 20, A 39, here A 14. But what is N? 20. Number of neutrons are same, right? No doubt. In our previous example, we wrote it as K1939. Just help me. K1939, K1940. What is they known as? If we are having 1939 and 1940, what are they known as? Isotopes. Here we are having it as an isotones, right? So that is our third factor. And the fourth one that we are having it, again we will put it iso word same. Iso electrons. This is much easier to understand. This time number of electrons are same, right? Okay, now here I can't write it as specific word atom is having same number of electrons, because no two atoms can have same number of electrons. No two atoms can have same number of electrons. If you want to make the same number of electrons, you can go it either for two different ions or between atom and ions. So here atoms and ions having same number of electrons. See what I told? Two atoms. I can't have it. I can never have same number of electrons. Atom can be compared with ion can be compared with ion. For that case, let us take it as an example. If we take it as an particularly an example of same number of electrons, oxygen 8, 16. I can't have it any other atom which can have 8 electrons. I can't have it atom. I can have the ion. I can have it as an in the form of oxygen. I am having it as an 8 electrons. We can have it as an another one having an 8 electrons like N minus. The ion we are having it as a N minus. That means 7, 14. Let's check whether they are having it or not. Protons 8, neutrons 8, atomic mass 16, electrons 8, proton plus, it's a neutral charge, so it will be 0. So you will be getting it as an here 8. For this proton you will have 7, neutrons 7, atomic mass 14, but electrons 8, because 7 plus 1, right? So you will get it as 8 electrons. Similarly, we can have it as a, not necessary that it will be a negatively charged only. We can also have it as an, in certain examples, with a positive charge, Na plus, Mg plus 2, or take it as a neutral atom also. See, positively charged with neutral atom. Two ions can be there with the same electrons. If I don't write it neutron, still they are isoelectrons. If I am writing neon, still they are isoelectrons. What does it show? Here we will be having it as an 11, 12, here it's a 10. So if I calculate it here, electrons, it's a proton minus charge. We will be getting it 11 minus 1, 10. Here also positive charge, so we will be getting it as 12 minus 2, that is equals to 10. Here it's a neutral, so 10. Right? So all the three atoms are having 10 electrons. Okay. Another example. In this, let's take it as K plus. We are taking it as K plus. Another one is argon, and the another one is S minus 2. See, one is positive, one is neutral, one is negatively charged. Still they are having same number of electrons. So what does we are going to get it here? Charge, electron is equals to proton minus charge, because it's a plus, so we'll get it as minus charge. We'll get it as protons. For the potassium, it's a 19 minus 1, 18. Here argon, it's a neutral, so electrons we are going to get it as 18. Here electrons we are going to get it proton plus charge, that is 16 is an atomic number, plus 2, that means 18. All the three of them are having 18 electrons. So same number of electrons, right? But very carefully make it sure that you don't make an error. Two atoms can never have same electrons. It can be two same positive charge ions, it can be two negatively charged ions, it can be two positive and negatively charged ions, or maybe charged and neutral atom. They can have an same number of electrons in them, right? So all these are the four terms that you have to remember: isotopes, isotones, isobars, and isoelectrons. Okay, after studying this, the structure of atoms, that we came to know it, the fundamental particles like protons, neutrons, electrons, that we want to discuss. Our next point for it is again a different scientist worked on them, and they tried to understand that what are these atoms or particles, or why they were termed as particles. At the same time, it was a scientist, they also proved it, that we consider them as dual nature. Dual nature means these protons, neutrons, electrons, they are not steady. What happens? So for them, dual nature word was being used. What does this dual nature wants to indicate? This dual nature wants to indicate that these are going to behave, these small subatomic particles, protons, neutrons, or whatever the subatomic particles are there, they behave as a particle, they behave as a wave. That means they are the waves, they go in a certain moments, as well as they are having mass. We know that components which are having in mass, they are known as particles. They are moving within certain velocity, so they are waves, right? So different scientists, they worked on it. The different scientists, I am using the word because here we are going to study many scientists, the name of the scientists and the formulas derived by them. We are going to study about Planck's equation, we are going to study about Einstein equation, Hertz equation, or Rydberg's equation, many other scientists, Lyman, Balmer, Paschen, Brackett, Pfeffer's, like this. The number of scientists have worked behind to find out these characteristics or the structure of atom, right? So in this case, the structure of atom, we want to prove it that it's a wave as well as particle, right? Now first of all, for this, very easy for us, because we know that when we want to prove it as a dual nature, it's a electromagnetic radiations, right? Now whatever the rays, if you say it as sunlight itself as an example, it's coming, traveling a very long distance, right? It's coming in the form of waves. They are also having it as in some mass present in them. So it was the first of all electromagnetic waves, radiations. They were considered to be as a waves. Now electromagnetic word is used because these waves are affected by both electric current or magnetic field. That means when these waves are allowed it to pass through only specifically a magnetic field. This is one of the diagram that is shown in your textbook. You can see it in your textbook, right? Only under the effect of magnetic field, when they are coming it, these rays, they cannot travel in a straight line. They divert themselves. They change their path. In place of this, if we put it as an electric field, if I am putting it as an electric field, and if these rays are allowed it to pass through it, they don't divert it into the same direction. They divert themselves into the opposite direction. In the electric field, their angle changed. Magnetic field, they went into the downward direction. But when both these are applied at a time, electric field is also there as well as magnetic field is also applied at the same time, their path does not changes. That means under the effect of both electrical and magnetic field, they are having it as a same path. So in our textbook, this diagram is shown to us that these radiations are allowed it to pass through it, magnetic field, electrical field, then it's shown like this. The diagram is shown like this. So this particular is for electric field, this is for magnetic, and this is in the neutral condition, right? So these radiations, they are changing it. But these radiation, when they are moving it, they are moving with a certain frequency. Certain frequency means you already know it. They move with certain frequency, right? This is the one point which we consider it as one frequency, right? The distance between these two, we name it as wavelength, right? So frequency, is sorry, inversely proportional to the time. That means we say that within a certain duration, how many number of crust or trough have been passed, that we consider it as frequency. Frequency we also write it as, this I am writing it as an nu, right? It's a nu, nu. What does it indicate? It's a inversely proportional to wavelength. It is also inversely proportional. Here we will be getting the formula nu is equals to 1 by time. Here we are getting it as the another possible, that frequency is also inversely proportional to the wavelength. If your wavelength is small, more amount of the frequency will be there. If the wavelength is bigger, less frequency. If I remove the proportionality sign, I am going to get it here C by lambda. So this is the one formula, this is the one formula on which we are going to have it as in sum. We also write it as wavelength is equals to C by frequency, right? Okay, now what is C? What is C? C indicates over here as velocity of light. C is going to indicate over here as velocity of light, right? So we are getting it as an frequency, wavelength and time having a relation which helps us to know the wave nature, right? This is the first nature that we discussed it. That's enough for today's lecture, right? We proved it. First of all, isotopes, isobars, isotones, isoelectrons. Make a practice of it, or the questions might be there for you. The second factor, we proved it that these are the radiations, right? We want to prove it dual nature. It's a very long topic, so we will take it, the rest of it, in the next lecture, where we will prove it as it's also a particle nature. Thanks.